Okay, exponential decay in a nutshell. Let's look at, we had exponential growth. We talked about zombies growing, doubling, 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 how long it takes. Let's talk about something getting smaller and smaller and smaller. So let's say I start off with 100, I don't know, 100 cookies, and I eat half of them a day. The first day, I eat how many cookies? 50. Good. So I start off with 100, then day one, I'm down to 50. And then after day two, I eat half of that, which is 25. So I'm down to here. And the next day, on day three, I'm down to here. And now I get partial cookies, but that's fine. And then down to here, half as much, half as much, half as much. And you notice what's going to happen is I'm going to have something that gets smaller and smaller and smaller and smaller and smaller. And if I only eat half of what I have each day, I will technically never have no cookies, which is horrible English, but weird math also. If something gets halved and smaller, there'll always be something there. Anyway, exponential decay is based on the same principles of exponential growth. We still use y equals ab to the x as our general equation, a being our initial value. So in this case, you'd have cookies of 100 to start off with. B is the decay rate now. Now, most decay rates we use either as a fraction, so you can use a fraction like a half, or as a decimal, which might be a little easier. Either way, this has to be less than 1. If you multiply anything by something less than 1, that first amount will get smaller. So 100 times something less than 1 is smaller and smaller and smaller and smaller and smaller. And x is the number of time periods. So here, if I want to figure out how many cookies were left at 4 days, I take my 100 cookies and I'd multiply it by a half, or 0.5, and to the power of 4. Throw that in the calculator and figure out how many cookies are left. Okay. And real life, don't forget, real life questions, do we consider decimals or not? You know, if we're talking about money, usually we just include in our answer a couple of decimals too. We talk about things that are weighed or measured. As many decimals as you can handle are fine, okay? But if you're talking about cookies, or we're talking about like how many gorillas, this is the number of gorillas that there are in the wild. Don't give me an answer like there are 2.7 gorillas left, because like I said in class, nobody wants to know what 2.7 gorillas looks like, okay? So be careful on your answers. The key to this really is what trips kids up is when you're doing decay. So the example we use at the start of, let's look at example 2 from our notes. You have $1,000 bike, cost you $1,000, and it's worth 8% less, or it depreciates at a rate of 8% per year. Now this comes up a lot with cars and other assets. If you're an accountant, for example, what you have is something called depreciation of assets, and that actually turns out to be pretty helpful for you, because if you go and you buy, you know, $10,000 worth of computers, you can each year write off a good chunk of this as an expense and not pay taxes on it, reduce your tax bill. So depreciation is actually in the accounting world, it's actually a good thing because it saves you money on taxes. But in real life, cars are worth less over years. And let's look at this bike. The bike examples that we depreciate 8% per year. So you have your 1,000, that's your initial amount, and then you have whatever. So if I want to say, hey, what's this bike worth in 6 years, which is the second question, it's going to be something to the power of 6. And initially, what people do is they go, okay, it's 8%. I want 8% of that. Well, right away, you lose 8%, right? But that's not how we set this up. If you set this up after year one, 1,000 times 0.08 is going to get you $80, and that's how much you lose. But you don't want to know what you've lost, because after the first year you're in big trouble. Now you could subtract that, but just like the exponential growth questions, you don't want to be multiplying and subtracting, multiplying, subtracting, multiplying, subtracting, when you can in fact multiply and subtract at the same time. So instead of saying I lose 8% per year, okay, you want to figure out how much you save. So if you lose 8%, 92% remains, okay? And this is a big deal when you talk about how much hair you have on your head after the age of 40. Okay? You don't care how much you lost. You want to know what you can do before you have to start doing some very strange things to make sure that it looks like you have hair on your head. So if you're down 8%, you have 92% remaining. Okay, so let's be positive about this. Okay, 92% sticks around, and that's your equation. Initial value, 1,000. 92% remains, or 0.92% remains, and then your time, number of compounding periods goes here. So in my $1,000 bike, 92%, 8%'s gone. In 6 years, I have whatever I have, okay? You look at other things like this. If the question's already given to you, like it is in example number 4, you have $15,000, and it says that you have an equation set up like this to figure out how much a computer depreciates per month. Be careful here, per month. If 95% remains, that means 1 subtract 0.95 or 0.05 or 5% depreciates. So that's a depreciation rate of 5% per month. The only other question that you'd be concerned with really is percent questions that are have to do with what percent is remaining. And what I'm talking about there is the caffeine question, example 3. If I drink some caffeine, and this is used for drug testing, so if you want to not get caught, you're on steroids and your name's Barry Bonds, and you want to not get caught by the people who can catch you and say, hey, don't do steroids. What you can do is you can make sure that the steroids get out of your body at a fast enough rate, or that you take them early enough, or don't take too much so you don't get caught. So for example, we use caffeine instead of steroids, for example, and we said if you depreciate at 13% per hour, when can you get to how much is left in 5 hours? Okay, so what I was saying before is if you know that they test at this rate, let's say they can figure out a parts per million of a certain amount here, you can take enough steroids early on, or not you, but Barry Bonds could have taken enough steroids early on, or an Olympic athlete can take enough steroids early on and have it come out of their body, and only a little bit remains. And if they test, they can only detect numbers above here, okay, anything above here. If you get below here on time, then you don't get caught. And what happens is and how do you catch these people? What you can do is either fix your testing, like lower the bar, or test at random periods. So instead of saying, hey, you're going to be tested on this day, we randomly test you and we catch you like this, okay? So that's the whole drug in your system example. And we'll use caffeine as the drug here. And if it decreases at 13% per hour, that means that 87% remains. So it's 100 subtract 13 gets you 87%, which is 0.87. Okay, so 0.87 remains, and you have a b to the x. And then if I don't tell you how much you've ingested, like how many milligrams or whatever the caffeine is measured in, if we just do an example, like what percent is left, well, the initial amount, okay, so 0.87 is your B, and then your hours. So if I wanted to know how much is left in 5 hours, I put 5 here. The initial amount is 100. And the reason we say 100 is that it's what you've taken, or 100%. So if I say what percent remains after 5 hours, we start at 100, we keep 87% per hour, and we go 5 hours. Okay, so that's what you put in. Anytime you're asked about the initial percent, what remains, and you don't have an amount, you start with 100 as your 100%. Okay, so that's that. Enjoy.